Today we're going to talk about an arithmetic series. Let's start off by reviewing an arithmetic sequence. 2, 5, 8, 11 would be considered a finite arithmetic sequence because it starts and it ends with a certain number. However, if we have 2, 5, 8, 11 and then ... that means it keeps going forever. And in this case, we just keep adding 3 forever. That would be an infinite arithmetic sequence. Now, the difference between a sequence and a series is that in a series, we're actually going to add the numbers. So 2 plus 5 plus 8 plus 11 plus, and if we kept adding forever, that would be an infinite arithmetic series, but we wouldn't have a sum because we could keep adding 3 forever. However, if we have a finite arithmetic series, such as 2 plus 5 plus 8 plus 11, we do get a sum, which is 26. Now, back in the 1700s, there was a boy named Frederick Gauss, and he was a very smart individual. And even at an early age, he could add numbers very quickly. Now, his elementary school teacher wanted to give the kids an assignment. So he wanted the students to add the numbers 1 through 100. So we have something like 1 plus 2 plus 3 plus, and then we would go all the way to 98 plus 99 plus 100, and all the numbers in between, of course. And the teacher figured it would take the students a while to do this. However, Frederick was done very quickly. Now, how did he do it? Well, he figured out that if he took 1 plus 100, that would equal 101. If he took 2 plus 99, he got the same answer of 101. And again, 3 plus 98, he would again get 101. So he ended up figuring out that he would have 50 pairs of 101. So we'd have 50 pairs of 101. And so he simply multiplied 50 times 101, and he got 5,050. And he was finished. Now, his teacher didn't really understand how he could do it so quickly, but Frederick had found a pattern there. So what did he really do? Well, he had to add up 100 numbers, but it turned out that it was 50 pairs. So if we take 100 divided by 2, that's our 50 pairs. And of course, the number that he added was essentially 1 plus 100. Now you say, well, yeah, but he did 2 plus 99. That's the same value of 101. And again, he ended up with 5,050. Now we can consider 1 as a sub 1 and 100 as a sub n. And then n is equal to 100. In other words, there was 100 numbers to add. The first number was a 1 and the last number was a 100. So we basically have a formula that we can come up with here. So if we take s sub n is equal to a sub 1 plus, and then we keep adding 1 each time, so that would be the first number, which is a 1 in our case, plus the difference, which is also a 1. And then we can keep doing this pattern, and then we would have a sub 1 plus 2 times the difference. So that would give me the 1 plus 2 plus 3, and we can, of course, keep doing this all the way until we get to the last number, a sub n, which was 100. We could also do this backwards. In other words, what if we started with 100, which is a sub n, then we would add 99 next, and then algebraically we'd say that would be a sub n, which is 100, and then minus 1. That represents the 99. Or we could do it with the 98. That would be a sub n and then minus 2d. Now this should have been d right here, so I'm going to change that to a d. D is 1. However, for the purpose of this, we need it to be just the difference. And then we can keep doing that all the way until we get back to A sub 1. Now, from an algebraic standpoint, if I was to add these two together, I would end up with 2 times S sub n, 2 times S sub n, and that would equal. Now, here's what happens here. A positive d and a negative d cancel out. Positive 2d, negative 2d cancel out. So what we end up with here is a whole bunch of A sub 1s plus A sub n's. Matter of fact, we'd end up with 100 of them going on down the line, because we have A sub n here, A sub 1, A sub n, A sub 1, and then finally A sub n, A sub 1. We'd have 100 of them. Now, in this case, we're going to say 100 is just n. If we divide both sides by 2, here, I'm going to end up with this formula right here. S sub n is equal to n times A sub 1 plus A sub n divided by 2. Now you might see other forms of it. It might just be n divided by 2 here, and then A sub 1 plus A sub n, or you might see it as n times A sub 1 plus A sub n divided by 2 in the inside there. It's really the same formula no matter how you look at it. So, of course, for our particular formula, we had 100 terms, and we said, okay, we'll take 100 divided by 2. That's how we got the 50. We had the 1, which was A sub 1, plus 100, and of course, we ended up with 5,050. So that's how Frederick Gauss did it, and therefore that's why we have the formula that we have today. We have to look at something else, though. There's something called sigma notation. So let's look at that real quick. Sigma notation, also referred to as summation notation. So let me go ahead and do that. That's going to be also referred to as summation notation. And what we have is the Greek letter, capital letter sigma, and it looks like this. This is the capital letter sigma, and I'll go ahead and write that. That's what it is. And when you see that in math, it literally means, I'll put it in quotes, it means find the sum. So when you see that, you're supposed to find the sum. So if we think of our previous example where we had to add the first 100 numbers, 1 through 100, we would put a 100 here. And it doesn't matter what variable I use. I'll just use the variable k. Sometimes you'll see the variable I or j. That doesn't really matter. And I'm going to put a 1 right here. So what that tells me is I'm going to start with 1, and I'm going to keep adding numbers until I get to the 100th number. Now in this case, I just have a rule of n. In other words, the difference is 1 each time. So basically this gives me 1 plus 2 plus 3 plus all the way to, like we said before, 98 plus 99 plus 100. And of course our answer was 5,050. So let me give you a different example with a different rule. So in this case, we're going to have, we'll start with the sigma notation here. I'll put a 12 right here. So we've got 12 different numbers to add. And I'll use the letter I. Sometimes I use the letter I is equal to 1. And now we have a rule. The rule is 7I plus 2. So that's our rule right there. So basically, that means find the sum of the 12 terms. And I'm going to apply that rule to find A sub 1. I need A sub 1, they're the first term. So that's going to give me 7 times 1 plus 2, which equals 9. So I'll use that in a minute. and then I need a sub n, which is really a sub 12. So that means I have 7 times 12 plus 2, which gives me 86. So I use the 86. Now, what this really means is I want to find the sum of the 12 numbers. And again, if I use my formula that we came up with, that's going to be 12 divided by 2 times, I've got my 9, which is a sub 1, plus my 86, which was a sub n, or a sub 12 in this case, because we have 12 numbers to add together. And if I just put that in my calculator, I end up with a grand total of 570. That would be the sum of those 12 numbers, which are found by applying this rule right here. Now, there will be a circumstance where you may not know a sub n. So recall that a sub n can be found by taking a sub 0 and then adding the difference times n. So therefore, if we needed to, we can modify our formula. S sub n is equal to n divided by 2 times a sub 1 plus, and then we can take this a sub 0 plus d times n. And of course, that would substitute for, all of this would substitute for a sub n, if necessary. So that concludes our video on arithmetic series.